So before we move on to the problem solving section of this unit, we need to start talking about these things called free body diagrams. A free body diagram is simply just a diagram that shows all of the forces, including magnitude and direction, that act on an object. So it's just a picture that shows us all the forces in their vector form, magnitude and direction, that act on an object. So if you have a book on a table, we've talked about this in the last video, there's going to be certain forces that are acting on it. First of all, we have the force of gravity, because this book is on Earth. It's going to experience that force. But also it's being supported by the table, which is our normal force. So a free body diagram is essentially just this picture I drew, but a little bit simpler. When we talk about free bodies, what does that free body term mean? Well, in this example, the book would be my free body, because the free body is just the object that's in question. So the book is sitting on the table. The book is our primary object. We're going to free it or isolate it from all the other objects around it. So in order to draw a free body diagram, there's different steps that we need to take. Our first step is we want to identify all of the forces that are actually acting on that object. And in order to identify them, we have to ask ourselves a couple different questions. So first of all, is it on Earth or on the moon or on any other planet? Because if it is, then we're dealing with the force of gravity. So again, it doesn't have to be the Earth, but any kind of big planet. Next up, is it touching a surface? Because if it's touching a surface, like the table with the book over here on the left, then we're dealing with a normal force. We know the normal force is that support force from a surface. Third question is it moving? If something is moving, it's very safe to assume that there is friction involved. This is kind of a very technical thing here. We'll talk about friction later on, but we can assume if something's moving that there is friction. Our next question, our fourth question is there a rope or a string? Because if there is, we know that we're dealing with tension. We know the force of tension is that force that's in a rope or in a string. Finally, is something or is someone pushing or pulling on the object directly? We know that that is the applied force, the force applied by something or by someone. So that's our first step, just identifying all the forces that are actually acting on the object. And then our second step is to determine the direction of those forces. So for example, we know that the force of gravity always points down. We know the force of friction always opposes motion. The force of tension is in the direction of that rope or string. Our third step is to actually draw the forces as arrows or as vectors with some magnitude and direction to identify how strong those forces are acting. So we're going to take a look at a couple different examples here to practice this process of drawing a free body diagram. So our first example is that we have a book sitting motionless on a table. So before we go through this process, just really quickly want to remind everybody that we are in the unit of balanced forces, which means in every single example that we do, every problem we solve in this unit, all of the forces acting on an object are going to be balanced, and we'll see different examples of this. But it's important to keep in mind when we're drawing our free body diagrams that those forces are going to be balanced, and we'll see what that looks like here. So if I've got a book on my table here, I know that this book is on Earth because I haven't been told otherwise. Our whole experience is on Earth here. So we've got the force of gravity for sure. Also, the book is touching the table. That's a surface. We've got the normal force. To determine the direction of these forces, okay, we know that this book is sitting motionless. Neither of these forces can be winning. Okay, it would be moving if either one would be winning. So in order to determine the direction, we know the force of gravity always points down. We know that the normal force is perpendicular away from the surface. So if I want to draw my free body diagram, we like to abbreviate that as FBD. If I want to draw my FBD, then I'm going to draw just a box to represent my object, just a simple box for my book here. I know that the force of gravity is going to pull down on my book. So it's going to point straight down. That's my force of gravity. I'm going to label that arrow as the force of gravity. And then I know my normal force is going to point up. The table's pushing up on the book. So that's my normal force. Also, since we're in the unit of balanced forces, like I just said, that means that the normal force has to be balanced with the force of gravity so that the normal force is equal and opposite to the force of gravity. So what I can do is just draw those little lines on my arrows to signify that they are of equal magnitude. They're the same length. Kind of looks like they're the same length, but those two little dashes just remind me that they are the same length. So when we draw our free body diagrams in this unit, we're talking about balanced forces. So when we draw our forces as arrows, it's really important that we make sure that they are balanced, okay? This book isn't going anywhere, which means that those forces have to be balanced. Not only do they have to be balanced up and down, they also have to be balanced left and right. And we have that here. There's no forces left or right, and our up and down forces are balanced. They're of equal magnitude. They're going to basically cancel each other out because this book isn't moving. Our next example, a person is pushing their couch across the carpet at constant velocity. So that's my best drawing of a person pushing their couch to the right across the carpet, which is kind of bumpy. Okay? We know this couch is on Earth. They haven't told us otherwise. We've got the force of gravity. It is touching the floor. The couch is, so that means that's a surface. We've got our normal force. We've also have a moving object this time. Our couch is moving. So we're going to have the force of friction. Friction's gonna want to oppose that motion. There's no rope or string, but we have an actual person who's doing the pushing, so that's going to be the applied force. So we'll talk about directions here first, but again, we want to keep in mind that all of our forces are going to be balanced. This object is moving at a constant velocity. So if I want to draw my free body diagram, I'm going to draw a box, a simple box just for my couch, so I don't have to replicate that drawing. I know the force of gravity is going to be pulling down on my object. So I've got the force of gravity pulling down. I know that the normal force is going to be pushing up. The floor is pushing up on the couch. I know those two forces have to be equal and opposite. Also, I know that friction opposes motion. Since friction opposes motion, we're moving to the right, which must mean that friction is pulling back to the left. Friction doesn't want me to be moving this couch. So the force of friction is going to point to the left, but my person is pushing to the right. So the applied force is going to be to the right. Also, we are in the unit of balanced forces, which must mean that the force of friction and the applied force are equal and opposite to one another. So I'm going to do two dashes to signify that they're different than the normal and gravity forces, but they're equal and opposite. So again, this object is moving at constant velocity, which is good. That's what we want when we have balanced forces. Okay, none of these forces are winning. Like if we had a bigger applied force, if the person was pushing harder, then the applied force would be winning and we would have an unbalanced force. We know from Newton's second law that an unbalanced force results in an acceleration, and we can't have constant velocity and acceleration. So F equals ma. If we have an unbalanced force, we must have acceleration. Okay, but we don't. We have constant velocity here. Constant velocity tells us that those forces have to be balanced. Our applied force has to be equal and opposite to our force of friction. Next example here, we have a disco ball that's hanging from the ceiling by a rope. That's my best little drawing there. To identify the forces, first of all, it is on Earth because we haven't been told otherwise. So we've got the force of gravity. It's not touching a surface. It's not moving. I guess it could be rotating, but it's not moving up, down, left, and right. But there is a rope or a string this time, which means we've got the force of friction. But nobody's pushing this, so no applied force. We know that the force of gravity always points straight down, pulls straight down into the earth. The force of tension is going to point along the rope. So we're going to keep that in mind as we draw our free body diagram here. I'm just going to draw my disco ball as a small box. I have the force of gravity is going to point straight down, as usual, same thing. I have the tension force as well. Well, the rope must be pulling up on the disco ball to support it, right? So it doesn't come crashing down to the floor. So that means my tension is going to be pointing up as well. So there's my force of tension. Also, I know that the tension force and the force of gravity have to be equal and opposite because we're dealing with balanced forces. Okay? If it wasn't balanced, then the force of gravity would be pulling the disco ball down to the ground, crashing, or it would be going up into the ceiling. Okay? Our next example is a box is supported by a string on an inclined plane. This is kind of a tricky one. I have the force of gravity because this box is on Earth. We haven't been told otherwise. It is touching a surface. It's touching that floor, that floor that's at an incline. So I have the normal force. It is not moving. I don't have to worry about friction. Is there a rope or a string? Yes, there is. I do have tension here. It's being supported by that rope, but nobody's pushing, so I don't have the applied force. We know the force of gravity always points straight down. We know the normal force is going to point perpendicular away from the surface, and the tension force is going to point along the rope. So when I draw my free body diagram, what I'm going to do here is, since the box is like at an angle, since we're dealing with this like inclined plane, I'm going to draw the box the same way it appears in the drawing just to help me. I could draw it the regular way, but you'll see why here in a little bit. Again, I want to draw it the same orientation just for my own brain. You can draw it the regular way though if you want to. We know the force of gravity points straight down. This is just practice at this point, okay? The normal force is going to point perpendicular away from the surface, but since the surface is at an incline, at an angle, then our normal force is also going to be pointing at an angle. So now the normal force and the force of gravity are not equal and opposite because that normal force is kind of at an angle. Okay, it's no longer pointing straight up, it's kind of up and to the left. Okay, so now I'm not going to draw those lines to signify that they're the same magnitude. In terms of the tension force, that rope is kind of pulling up and to the right on the box. It points always along the rope, so that's going to be that way. And now you can kind of see maybe why I didn't draw the box like straight horizontal, where I kind of drew it at an angle, because I could draw all of the forces the same way on this box. It just kind of confuses me with like the angles and stuff, because what do we see here? We see that the force of gravity would point like not straight down, and that kind of confuses me. Like if you just rotated the box to be like the incline, then you see it's just easier for my brain, is what I'm saying. So I would always draw it like this, the way I have it on the left. But that's our free body diagram for this inclined plane. Our last example here is a block of ice is sliding along a frictionless surface at constant velocity. So ice on ice, let's say. Okay? We are told that it is a frictionless surface. We have to keep that in mind here. However, going through our questions, is it on Earth? First of all, yes, our ice is on Earth. We haven't been told otherwise. Is it touching a surface? Yes, it's touching that surface, whatever it's on, ice, let's say. It is moving, so we could consider the force of friction. However, they literally tell us in the problem that it's a frictionless surface, so there's no friction in this problem. We know the force of gravity points down. We know the normal force points straight up, away from, or perpendicular, away from the surface. So when I draw my free body diagram, I'm going to draw a box to represent my ice block in its same orientation that we see it in the picture. I know my force of gravity is going to pull straight down, same gig. I know my normal force is going to point perpendicular from the surface, which in this case is straight up, and they must be equal and opposite because this ice isn't falling down and it's not flying up, so they have to be equal. Neither force is winning. So you might be asking yourself, well, isn't there a force that's like pushing this ice? But if you consider like an air hockey puck, Okay, an air hockey puck can just kind of glide across the surface without anything pushing it. Something must have pushed it to start it, but it's not constantly pushing on it. So you might be thinking, like, there must be an applied force to the right, because this block of ice is moving to the right, but nothing is touching it. There's nobody who's pushing it. It's just moving along the surface at a constant velocity. Okay, it's just gliding along by itself. So something must have pushed it, but we're not interested in that. We're just looking at it right now where nothing is pushing it, and it's just sliding along at constant velocity, and we have balanced forces up and down and left and right. And that's free body diagrams.